Good evening, everyone. Welcome you all to the problem solving session of NPTEL course on ice engines and gas turbines. I am Pradeev E. I am one of the TA for this course. I will conduct the problem solving sessions on Tuesday 6 to 8 p.m. I will record this session, and this will also be uploaded in YouTube, and the link to the the video will be shared to you through the NPTEL portal. Uh, can someone Can someone confirm that you are able to listen to me?
Yeah, sir. Yeah.
Okay.
Yes, sir.
Thank you. Okay, I will start with the first problem. The cubic capacity of the 4-stroke over square spark ignition engine is 245 cc. The over square ratio is 1.1. The clearance volume is 27.2 cc. We have to calculate the bore stroke and compression ratio of the engine. So can someone explain what over square engine means?
D is greater than L, sir.
Yes, so D is greater than L. So when they say the over square ratio, then it should be D by L is 1.1. Now starting with the displacement volume, so we have displacement volume
Scientific calculator.
pi by 4 D square L. Can you mute yourself? You can unmute only when you want to interrupt. Thank you. Now we have this writing in terms everything in terms of D. We have L is D by 1.1. So we have pi by 4 D cube by 1.1. Now this is given as 245. So to calculate D, we will have D cube will be 4 into 1.1 into 245 divided by pi. So D will be cubic root of Can someone answer the
So 7 centimeters.
Yeah, so this is this is 7 centimeter. So that means L will be D by 1.1. So that is 7 by 1.1. Can someone answer this?
So 6.36.
6.36 centimeter. Now we want to calculate the compression ratio. Compression ratio is stroke volume.
Total volume by clearance volume.
Yeah, by total volume by clearance volume. So total volume is swept volume plus clearance volume. So now we know that this swept volume is 245 cc and clearance is given as 27.2.
So 10.
So compression ratio is 10. Can we move to the next problem, or if you have any questions, we can I can answer now. Okay, we will move on. So the second problem, we have given the mechanical efficiency of a single cylinder 4-stroke engine, which is 80%. The frictional power is estimated to be 25 kilowatts. Calculate the indicated power and brake power developed by the engine. So we know mechanical efficiency. Sometimes this application gives problem. Yeah. So eta mechanical is given as 80%, which is brake power by indicated power. We know indicated power is brake power,
BP plus FP.
yeah, brake power plus friction power, and friction power is already given, so friction power is 25 kilowatt, and this is 80%, that means 0.8. Now we need to calculate brake power and the indicated power. So here we know brake power by brake power plus 25 is 0.8. I think someone is unmuted. 0.8 times of brake power plus 25.
Sir, 100. Brake
Brake
power.
power is 100.
Yes, sir.
Okay, anyway, for the so that everyone will understand, I will write the steps. So we have 0.2 brake power is equal to 0.8 into 25. So brake power is 4 into 25. So that is 100 kilowatt.
Sir, indicator power 125.
Okay. So yeah, indicated power, as we said earlier, it is brake power plus frictional power, so that is 100 plus 25, which is 125 kilowatt. We have brake power. Any doubts in this problem?
No, sir.
Okay. We'll move on to the next problem. So we have a 42 kilowatt, 42
One question from here. Like, will you be sharing all these solved problems or worksheets?
Yes, the notes will be shared in terms of in the form of PDF, and the link
Okay.
will be made available to you through the NPTEL portal. And also the
Okay.
video will be recorded now, and it will be uploaded to YouTube, and that link will also be given to you through NPTEL portal.
Oh, yeah. Thank you. Thanks for that. Yeah.
So in the next problem, we have a 42.5 kilowatt engine which has a mechanical efficiency of 85%. The indicated power and friction power has to be found out. This is similar to what we did earlier. If the friction power is assumed to be constant with load, what will be the mechanical efficiency at 60% load? So now find the indicated power. So we can start solving with the known parameters. 42.5 kilowatt engine means so that means brake power is 42.5 kilowatt, and mechanical efficiency is 0.85. Now
IP is 50 kilowatt.
okay, that's good. So mechanical efficiency is brake power by brake power plus frictional power, or we will write brake power by indicated power directly. So that means indicated power is brake power by 0.85, which is 42.5 by 0.85. So this is
50.
okay, 50 kilowatt. Now friction power is equal to indicated power minus brake power. Indicated power
7.5.
is 50 minus 42.5. This is 7.5 kilowatt. Now if the frictional power is assumed to be constant with load, what will be the mechanical efficiency at 60% load? So that means at new brake power, right, 60%, brake power 60 is equal to 0.6 into brake power, which will be 0.6 into 42.5. So we will have something here, and mechanical efficiency is given as 60%. So we have the same friction power, and okay. So what is this brake power at 60%? 0.6 into 42.5.
$25.5.
Yeah, so this is 25.5 kilowatt. Now the friction power is said to be constant, so that means at 60% load, the friction power is also the same, 7.5 kilowatt. Now mechanical efficiency is brake power by brake power plus friction
So
power.
77%.
Okay, 77%. So this is 25.5 divided by 25.5 plus 7.5. So this comes up to be 77%. Any questions with this problem? Deepak Kumar has shared a jam file. Can you ask your question if you have over audio? Okay, if there are no questions, I will move on. Find out the speed at which a four-cylinder engine using natural gas can develop a brake power of 50 kilowatt working under following conditions. So air-gas ratio is given as 9:1. Calorific value of the fuel is given as 34 megajoules per meter cube. Compression ratio is 10:1. Volumetric efficiency is 70%. Indicator thermal efficiency is 35%, and the mechanical efficiency is 80%. The total volume of the engine is 2 liters. So now we know that this is a four-cylinder engine, so that means each cylinder will have a displacement volume of 2 liters by 4, since it's a four-cylinder engine, so that is 0.5 liters or 500 cc. We have been given that the compression ratio is 10:1, so that means so compression ratio is 10, so that means we stroke volume plus clearance volume by clearance volume is 10, and we know that the stroke volume is 500. Sorry, I think already the total volume is given, so that means we have Vs plus Vc as 500. So that means Vc is equal to 50 cc, and that means Vs will be 500 minus 50, which is 450 cc. Now we know that the volumetric efficiency is given, which is 70%. So we know what volume of air has actually come in. So right, volumetric efficiency is 70%. So that means volume of air that has come in is 0.7 into the stroke volume, that is 450. So what is this 0.7 into 450? This is 315 cc. So that means during every suction stroke, only 315 cc of the air at atmospheric condition enters into the cylinder. Now we know air gas ratio, which is given as 9:1. So fuel air by fuel equal to 9. So that means we have volume of fuel equal to volume of air by 9. So that is 315 divided by 9, which is 35 cc. So for every cycle, every engine cycle, 35 cc of volume, 35 cc of fuel is given. So with that and with the calorific of the fuel, we know what is the fuel energy that is given in the cylinder for every cycle. So right, fuel energy is calorific value into V fuel, which is 34 megajoules per meter cube into 35 cc. So since this is in cc and I have to convert to meter cube, I would have I should multiply this with 10 power minus 6, right? Now this is in megajoule, so I can take out this 10 power minus 6 and put it in terms of in joules. So that is 1190 joules of fuel that is given in the engine for every cycle, for every cylinder. And we know that indicator thermal efficiency is given and mechanical efficiency is also given. So using these two efficiencies, we can calculate what would be the indicated energy from every cycle and every cylinder, and then we can also calculate the brake energy that is coming out for every cycle. So this is indicated thermal efficiency. Indicated thermal efficiency is given to be 35%. So this is fuel energy, sorry, indicated work by fuel energy. So So that means indicated work is uh, 0.35 into fuel energy, which is 1190 joules. Can you follow the problem, or so this is 416.5 joules of indicated work, which is coming from one cylinder for one cycle of the engine. So that means 4 strokes of the engine. Now we can calculate the brake work. Brake work is mechanical efficiency into indicated work. So that is mechanical efficiency is given as 80%. So 0.8 times of 416.5, that is 332 joules. Now we have been told that the engine can produce a brake power of 50 kilowatt using 4 cylinders, and so far we have been dealing with a single cylinder, and we need to find what would be the brake power. So brake power is equal to brake work per cylinder into number of cylinders into number of cycles per second. So this is in terms of joules, and this is in terms of per second. So we will get joules per second. So this is 50 kilowatt is 50 into 10 power 3. Brake work is 333.2 into number of cylinder is 4, and now we will get the number of cycles per second. So number of cycles per second is 37.51. Now to convert this to speed, that means it has to run 2 revolutions for every cycle. So number of revolutions per second is 37.51 into 2, that is 75.03, and so generally we say speed in terms of RPM, so that is 75.03 into 60. So we have RPM is revolutions per minute. So far we had a number of revolutions per second, so multiplying by 60 we get 4502 RPM. Any question, any doubts with the problem? I will go through the problem once. So we have to find the speed of a 4-cylinder engine which uses a natural gas that can develop a brake power of 50 kilowatt working with the following conditions. So the air gas ratio is given as 9:1, calorific value is given as 34 megajoules per meter cube, compression ratio is given as 10, volumetric efficiency is 70%, indicated thermal efficiency is 35%, mechanical efficiency is 80%, and total volume of the engine is 2 liters. So this is total volume. It should not be confused with the swept volume. And so assuming so since it is a 2-liter engine, 2-liter 4-cylinder engine, we have individual cylinders volume as 2 liters by 4, which is 0.5 liters or 500 cc, and compression ratio is given as 10. So that is 500 by compression clearance volume. So we know the clearance volume is 50. With this we can calculate we have the total volume and the clearance volume. We can calculate the swept volume, that is 450 cc. Using volumetric efficiency, we can find what is the volume of air at atmospheric condition that is going into the engine for every cycle. So swept volume is 450 cc and volumetric efficiency is 70%. So we get volume of air is 315 cc. Now we know that the air gas ratio is 9. So that means here the gas is a fuel. So volume of fuel is volume of air by 9. So that is 315 by 9. We have got it as 35 cc. And we can, using this, we can calculate the fuel energy that is going inside the cylinder for every cycle. So that is calorific value into the volume of fuel, which is obtained to be 1190 joules. And now we have indicated thermal efficiency, which relates the indicated work to the fuel energy that is applied to the engine at every cycle. So with this we can calculate the indicated work, which is 0.35 into 1190, and that is 416.5 joules. And brake work is obtained using the mechanical efficiency and the indicated work, which is 333.2 joules. Now we have the brake power, we have the brake work per cylinder per cycle, and we know that the number of cylinder is 4, and with this we can calculate the number of cycles that is required for every second. So that we have obtained as 37.5 cycles per second, and that means since it is a 4-stroke engine, we have 75 cycles per 75 revolutions per second, and that is around 4500 rpm. Do you have any questions with this problem?
No, sir.
So moving to the next problem, we have a 4-stroke 4-cylinder diesel engine running at 2000 rpm. This develops power of brake power of 60 kilowatt. Brake thermal efficiency is 30% and calorific value is 42 megajoule per kg. This engine has a bore of 120 mm and stroke of 100 mm. We can take a density of air as 1.15 kg per meter cube. Air fuel ratio is 15:1, and the eta m should be mechanical efficiency, which is 80% or 0.8. We have to calculate the fuel consumption, air consumption, indicated thermal efficiency, volumetric efficiency, brake mean effective pressure, and mean piston speed. Firstly, I hope that you are familiar with the terms like indicated thermal efficiency, volumetric efficiency, and so on. I think before going to this problem, let's see about the terminologies.
Excuse me, sir.
Yeah.
Sir, I think we have done these questions previous section.
The same question?
Yes, sir.
Okay. Actually,
Yet mean piston speed wasn't there.
oh, okay. But other terms are there.
Yes, sir.
Okay. The idea of NPTEL to have multiple sessions is that if someone is not able to attend on particular day, they can attend on a different day. But I will also try to bring different problems so that if someone is more interested and wants to attend all the sessions, will not get bored with the same problems. But I think there will be some other people who haven't seen this problem, and I just want to confirm if everyone is familiar with these efficiency terms like volumetric efficiency, mechanical efficiency.
No, better to go through, sir,
Yeah.
because I didn't attend yesterday's class. Sir.
Okay. So I would start with the brake power. Brake power we generally mention with BP, which is 2 pi nt by 60. So here n is engine speed and T is torque. So this torque is the brake torque, which is felt on the output of the shaft. And indicated power is IP, which is generally obtained by brake power plus friction power, and this can also be obtained by using mean effective pressure. We have P MEP into LAN by 60 into number of so this n is into capital N. So here the small n represents number of revolutions per cycle. So this would be 2 for 4 stroke and 1 for 2 stroke engine, and n is number of cylinder. L is the length of stroke length, A is the area of piston, and this n is speed. So I think we should write it differently. Write NC. So this is indicated power. So friction power is the difference between these two, and mechanical efficiency is defined as brake power to indicated power. So this indicated power is the power obtained by virtue of the gas pushing the piston downward, and because of the friction in every component like the piston ring, crankshaft bearing and other things, we will be able to only get some lesser power out of the shaft. So that is defined as brake power. And volumetric efficiency is this says how much of air we are able to effectively take into the cylinder. So in the denominator we have mass of air that can be at cylinder volume at atmospheric conditions or at manifold conditions. So the manifold can be of a higher pressure or lower pressure. If it is a naturally aspirated engine and a throttled engine like a SI engine, we might have 0.8 bar, 0.7 bar in the manifold. But in case of a SI engine, which is usually turbocharged, manifold pressure will be much higher, say 2 bar to 4 bar. And so as reference we have mass of air at manifold pressure conditions density, and for the cylinder of the volume of the cylinder, and in the numerator we have the actual air mass that is taken in. So if there is a if the poppet valve is very if the opening of the poppet valve is very low, or if there is only 2 valves per cylinder, like only 1 intake and 1 exhaust compared to 4 valves per cylinder, the volumetric efficiency will be low. And there are some other techniques by which the volumetric efficiency can be increased, which you might be seeing later in the course. Then we have brake thermal efficiency, which is brake power by fuel power. So here fuel power is obtained by calorific mass of fuel into calorific value of fuel. Similarly, we have indicated thermal efficiency, which is indicated power by fuel power. So here again it's lambda def into CV. did I miss any other efficiencies? Yeah, we have brake, mean effective pressure. So here I was just telling the mean effective pressure when I defined integrated power. So mean effective pressure, can anyone explain how mean effective pressure is happening? This is not covered in the this week's course, or okay.
Some of terms are not covered.
Okay. Anyway, I
Like
thought.
some of the questions are asked in the lectures which we will be attending. Right. In that lectures, we might can find these questions and these terms.
Okay. Okay. I would explain this. So
Like
mean.
in first week assignment, we were able to find those assignment answers in second week lectures.
Oh, okay. Then I
So
think you can
yeah,
submit
sir.
a feedback about this.
Yes, sir. I wrote in the feedback. Let's see what happens next.
Okay, okay. But anyway, I think many of these are very basics. Maybe if you haven't covered in your UG course, then it is really new for you. But most of the terms comes in the maybe third or some sixth semester itself. Okay, so mean effective pressure is defined as work done per cycle divided by displacement volume. So this work done is obtained by integral P dV by displacement volume, or yeah. So how do we obtain this integral P dV? Yes. So we have pressure volume. I think this you would have seen this pressure volume curve.
Yes, sir. Yes, sir. Yes,
So
sir.
assume this is 1 atmosphere, and for a naturally aspirated engine, as like an SI engine, we start from here uh, at this point, and during compression, during the suction stroke, the pressure will go down, and then
Yes, sir.
after during during compression goes high. Sorry, I think I stopped. This is volume at uh,
B
TDC.
TDC
This is volume TDC.
BDC.
Yeah, so we will start from this point. The pressure will be low during the suction stroke, and after attaining BDC and the intake valve is closed and it starts compressing, the pressure starts rising, and somewhere here we will have the spark and start to combust. So the pressure temperature will rise further, and then piston will go down, reducing the pressure, and then at this point exhaust stroke starts, and there will be a slight higher pressure. I think this is much exaggerated. uh, During the exhaust stroke, the pressure will be a little uh, higher than the atmosphere. So generally this volume, so this is volume 1 and this is volume 2. Volume, sorry, this is area 1. So area 1 and area 2. Area 1 should be greater than area 2. Here I have drawn, I have exaggerated the pumping loss here. So this is this loop on the bottom loop is pumping loss, because this work is done only to pump the air in and out, and this is compression expansion loop, this loop. So now for this work done, when I say integral PdV, it's like integrating the entire curve, this one. So that means it will have this area plus this area. So I have defined IMEP, and when we have mechanical efficiency, we can say it is BMEP divided by IMEP. So mean effective pressure is can also be defined like a imaginary pressure which is applied when it is applied constantly on the piston. It gives the same work output as the real cycle. And BMEP is just imaginary. We just multiply the IMEP with the mechanical efficiency and get the BMEP. So I think I have covered everything that is needed for this problem. And fuel consumption, air consumption will be known earlier. Now we can start solving the problem. We have a 4-stroke 4-cylinder engine running at 2000 rpm, develops 60 kilowatt. Brake thermal efficiency is given, calorific value is given. Okay. First we'll try to calculate the fuel consumption. So that means so we have brake power. Brake power is 60 kilowatt. Brake thermal efficiency eta PTE is given as 30%. So that means brake power divided by m dot f into CV, so that is fuel power in the denominator, is 0.3. That means m dot f is equal to, we have brake power which is 60 kilowatt divided by 0.3 into calorific value. Calorific value is 42 megajoule per kg. So I would write 42 into, having everything in SI units is better. So I will have 42 into 10 power 6 joules per kg, and in the denominator it was 60 kilowatts, so I would have 60 into 10 power 3. So can someone compute what m dot f is? M dot f is 4.76 into 10 power minus 3 kilogram per second. Now we know the air-fuel ratio is given as 15, so R is 15, so that means m dot A by m dot f is 15. Now we know m dot A, sorry, we know the m dot f mass of fuel. So to calculate m dot A, we have it as 15 into m dot f. So that is 15 into 4.76 into 10 power minus 3. So this is 0.0714 kilogram per second. So now next we can calculate the, so air consumption and fuel consumption are calculated. Okay, now air consumption is calculated in terms of meter cube per second. So we need to know the density. Density is given. With that we can calculate the air consumption in terms of volumetric fluid. So we had m dot a as 0.0714 kg per second. Density of air is also given, which is 1.15 kg per meter cube. So volume flow rate of air is m dot a by rho a, which is 0.0714 divided by 1.15. Can someone help me in this computation? Okay, it's yeah, understand, right?
62.09 into 10 power minus 3.
Yeah, you are right. So it is 0.062 meter cube per second. So we have calculated air consumption. Now we need to calculate indicator thermal efficiency. So we have the brake power and mechanical efficiency. So with this we can calculate the indicated power. So brake power is 60 kilowatt. I have mechanical efficiency as 0.8. Sorry. This is brake power by indicated power. So this is 0.8. This brake power was 60 kilowatt by indicated power. Indicated power is 60 by 0.8.
75 kilowatt.
Thank you. 75 kilowatt. Now to calculate indicated thermal efficiency, we have indicated power by fuel power, which is m dot f into cv. Indicated power is 75, having in terms of SI units, 75 into 10 power 3. For the m dot f, we had 4.76 into 10 power minus 3. Into calorific value is given as 42 megajoule per kg. Again I will 42 into 10 power 6 megajoule, sorry, joules per kg.
%37.5%.
Okay, so we have calculated the indicated thermal efficiency. Next we have volumetric efficiency. Yeah, so for volumetric efficiency we have been given the bore and stroke, and we know the volume flow rate, and we know the RPM also. So first I would calculate the displacement volume. Vd is pi by 4 d square L, which is pi by 4 into d is 120. I would write in terms of cc. So this is bore is 12 centimeter and stroke is 10 centimeter. So 12 square into 10. What is the displacement volume?
1130.4.
Hmm. 0.4 cc.
Huh.
So in terms of meter cube, we will have 1130.4 into 10 power minus 6 meter cube.
Minus 6 meter cube.
Yeah. So we know this, and we have the volume V dot A, that is the actual mass of air that is going in, is 0.062 meter cube per second, and we know the speed of the engine is given as 2000 rpm, and we have been told that it is a 4-stroke engine. So this is a 4-stroke 4-cylinder engine. So that means we will have one engine cycle for every 2 revolutions. So that means cycles per second is equal to 2000 by 2 into 60. 2000 by 60 will give me rotations per second, and by 2 will give me cycles per second.
.33.
I'm getting 16.67. 2000 by 120.
Yes, sir. Yes, sir. Yes, sir.
Okay. So now we have cycles per second, and we have V dot A. So this V dot A is mass of air going in per second. So to calculate uh, volume of air intake per cylinder per cycle is V dot A divided by cycles per second into number of cylinder. So here the total volume of air that is going inside the engine per every second is 0.062 meter cube as given by V dot A. So this is taken by 4 cylinders at the rate of 16.67 cycles per second. Okay, so we have in the V dot A as meter cube per second, and in the denominator we have cycles per second. So this will give me meter cube per cycle, right? Then again we have not considered the number of cylinders, so this is going in for all the 4 cylinders. So I want to calculate for a per cylinder volume that is going in. So that's why I have divided it by number of cylinders, NC, that is 4. So can you compute this? Can someone confirm if you are also getting this value 9.3?
Yeah, yes, sir. Yes, sir.
Okay. Now now we have the actual volume of air that is going in, and we have the displacement volume as here 1130 into 10 power minus 6. So we can calculate the volumetric efficiency, which is 9.3 into 10 power minus 4 divided by 1130.4 into 10 power minus 6. Is everyone following the problem? I don't know why you are not able to solve.
Yes, sir. Yes, sir. Yes, sir.
So, what is the volumetric efficiency? Okay, I think Nixon has already replied, so that is 82.26%. If you if others are not getting the same value, or if you have trouble understanding, you can let me know. I can answer individually. Okay, now volumetric efficiency is calculated. Now we have to find the break mean effective pressure. Okay, James Stephen is also able to answer. Break mean effective pressure and mean piston speed. Break mean effective pressure. As I told, mean effective pressure is here we had work done per cycle divided by displacement volume. When we have integral PDV, this will represent indicated work. As I mentioned, indicated terms are relating directly to the energy transfer from the gas to the piston, and it doesn't account for the friction in the components. So now brake mean effective pressure will have brake work divided by displacement volume. Or we can also make use of this indicated power formula, P MEP into ln by 60. So now with the brake power is 60 kilowatt at 2000 rpm for 4 cylinders. We can calculate what is the brake work per cylinder per cycle. Can someone explain how we can do this one? Like, how do we calculate brake work using brake power? Okay, brake power is so we will have we'll solve this equation for a per cylinder basis. So we have 60 kilowatt and for 4 cylinders, so we have On the left hand side we have 16 to 10 power 3 for a 4 cylinder. So per cylinder brake power will be 60 by 4 kilowatt, and we need to calculate brake work by cycle, and we have cycles per second. So we had 2000 rpm, which was 16.67 cycles per second. So we can calculate brake work per cycle.
Level of
Sorry. Yes. 8. I would approximate this to 900 joules per cycle. So now we have brake work and displacement volume. So BMEP is brake work. I think yeah, we have taken it already on cylinder basis. Brake work per cycle divided by displacement volume. So this is 900 joules divided by displacement volume is 1130 cc, 1130.4. This is for 4 cylinders, right? No, this is for a single cylinder itself. 1104 cc, and this cc to be converted to meter cube, since we should have everything in SI units. So what is BMEP? 1.017. What is the units? Directly this will give an unit of Pascal. I am getting 796,178 pascals. So this is 7.96 bar. Can everyone get the same value, 7.96 bar? Now we need to calculate mean piston speed. So mean piston speed. Can anyone tell me what is how can I calculate mean piston speed?
Don't know, sir.
Sorry.
Oh, we don't know, sir.
Okay. Yeah, 2 ln. So here L is the stroke length and N is revolutions, engine speed. So the piston moves up and down, and it moves by a distance of 2L for every cycle, right? Because for one revolution of the crankshaft, the piston moves from top to bottom and then bottom to top dead center to bottom dead center. When it moves from this point, when the crankshaft moves from this point to bottom position, and then again it will goes back to the TDC. So that means for every revolution of the crankshaft, the piston moves by a distance of 2 into stroke length. So that is 2L, and this happens in every second. This happens for every for the number of revolutions in a second. So that's why we multiply this with n. So we have the distance traveled in one crankshaft rotation, and this crankshaft rotation happens for n times in 1 second. So that means the piston is also moving in 2ln times per 2ln distance per second. So this is engine speed in terms of revolutions per second. So we have L is 0.1, right? Yeah, we have a stroke of 100 mm, so that is 0.1. Yes. And now engine speed is 2000 rpm. Converting it to revolutions per second, we have by 60. So what is the mean piston speed?
Forty.
40.
40 by 6. No, 40 by 6. Just wait a while, sir. Si- 6.67.
Yeah, 6.61.
6.67. 40 by 6 and 6.62. Yes, sir.
Okay. 40 is too high. I think even F1 engines won't have 40. F1 engines, for your information, it runs at say 20,000 rpm, and it has a the last F1 engine in 2022 had a displacement volume of 1.6 liters, 4-cylinder engine, and goes as high as 20,000 rpm. So for higher rpm we will have higher mean piston speed, and all the inertia has to be taken into account. The forces due to the inertia of the piston and the crank connecting rod and crankshaft should be sufficiently strong enough, and so on. And the balancing has to be very perfect on the crankshaft. Okay. Now, if you have any questions in this problem, I can answer now, or I can go to the next problem. Okay, I move on to the next problem. Single cylinder 4-stroke hydrogen fueled spark ignition engine delivers a brake power of 20 kilowatt at 6000 rpm. The air gas ratio is given as 8:1, and the calorific value of the fuel, that is hydrogen, is given as 11,000 kilojoules per meter cube. The compression ratio is 8:1 again. If the volumetric efficiency is 70%, indicated thermal efficiency is 33%, and the mechanical efficiency is 90%, calculate the cubic capacity of the engine. I think we have seen many similar problems. I think now we'll be able to tell me how we can solve this problem. Brake power is 20 kilowatt, and mechanical efficiency is given as 0.9. So we have this is indicate brake power by indicated power. So indicated power is 0.9 into brake power, which is 20. So this is 18 kilowatt. Now we have indicated thermal efficiency, which is 0.33. Indicated thermal efficiency is indicated power divided by mass of fuel into calorific value. This is 0.33, and so we have indicated power of 18 kilowatt. This is 18 into 10 power 3, and m dot f we don't know. We can find this out, and calorific value is given as 11,000 kilojoules per meter cube. So again, having this in terms of SI units, we will have into 10 power 3 joules per meter cube, into 10 power 3 joules per meter cube. So, and this cannot be m dot now because we have calorific value in terms of mass. So I would write this as v dot f, so that represents volumetric flow rate of the fuel. Now we can calculate volumetric flow rate, which is 18 into 10 power 3 divided by 0.33 into 11,000 into 10 power 3. Can someone compute this?
(4.95 into 10 to the power minus 3).
Yes, minus 3 meter cube. Sorry, meter cube per second. Right? So now we have the volumetric flow rate of fuel. With this we can calculate volumetric flow rate of air. So volumetric flow rate of air is we have been given air-fuel ratio, the air gas ratio. So yeah, right, air gas ratio. Air gas ratio is v dot A divided by v dot f. This is 8:1, and that means v dot A is 8 times of v dot f, which is 4.95 into 10 power minus 3. So this is
39.6 into 10 to the power minus 3.
again, this will be in meter cube per second. 39.6. Now we know this much of air and fuel has to be given into the engine, so that we get the target power of, say, brake power of 20 kilowatt and at 6000 rpm. Now I think now it is simple to calculate the cubic capacity. So we know the total volume, total flow rate V dot is equal to V dot A plus V dot F, which will be 39.6 into 10 power minus 3 plus 4.95 into 10 power minus 3. That is the total volume flow rate.
44.55 into 10 to the power minus 3.
Yeah. Thank you. Again, this is in meter cube per second. So I would write V dot 44.55 meter cube per second. Now, any idea how we can go with the problem? We have the total fluid volume flow rate that has to be gone in. We have the volumetric efficiency, and we need to calculate the cubic capacity. So volumetric efficiency is 70%. Before that, we can calculate volume. So we have the speed of the engine, so that is 6000 rpm, and I think we have been told that it is 4-stroke engine, 4-stroke engine, single cylinder engine. So that means 6000 into 2 into 60 cycles per second, right? So this is 100 by 2, which is 50 cycles per second. Now volume of fluid intake per cycle is volumetric flow rate in terms of meter cube per second divided by cycles per second. So seconds get cancelled, we will have meter cube per cycle. So that is 44.55 divided by 50. So this is 0.8.
0.891 into the 10 power minus 3.
How did you get 10 power minus 3? Okay, yeah, here we had 10 power minus 3. Sorry, I
Yes.
missed it. Yeah.
Yes, sir. This is missing 10 to the power minus 3.
So this is the meter cube fluid that has to go into the cylinder for every cycle. Now we have the volumetric efficiency, which is V fluid, I would say, divided by volume of displacement. So that is 0.7, right? What is the volumetric efficiency? Yeah, volumetric efficiency is given as 70%. So 0.7 is equal to volume of fluid is 0.891 into 10 power minus 3 divided by displacement volume is what we have to find. So V displace 0.891 by 0.7 into 10 power minus 3.
One 1.27 into 10 to the power minus 3.
This much meter cube. So that would be 1270 cc. So for the given engine operation, we need a 1270 cc displacement volume engine to generate 20 kilowatt at 6000 rpm. Is the problem clear?
Yes, sir. Yes, sir.
Okay. I will just yeah.
Sir, why we write this Indian size in centimeter cube? Since the SI system is
Yes. SI
meter cube,
system is
no?
in meter cube, but it will not be
Why?
very easy to write every time into 10 power minus 3 or minus 6. So 1270 cc is easy to say. That's why we use this in normal terms also. Like we say 100 cc bike engine, 1 liter, or if it is for passenger car engine, when it becomes more than 1 liter, we used to say it in terms of liters. 1 liter, 1.5 liter, or 2 liter engine. When it is very small, we say it in cc. That's just for easy to mention. Any other questions?
Sir, what is the function of piston ring, sir?
Piston rings.
Except wear and tear, what are the other function of piston ring, sir?
Okay. So the piston will be something like this. There could be like 3 piston rings. Right? Generally, the gas, ideally we need to seal it completely, and we should also keep the piston moving, right? So if we have the piston which is of diameter of the cylinder or the liner, we cannot move. It will be of very it will be very tight to move. So that is why we have this say if this diameter is 100 mm, we have this piston size manufactured at say 99.9 mm. So there will be 0.1 mm clearance in diameter, and then even this is ineffective because the gas can flow through this, and whenever we compress, some gas pass through the piston and comes to the crankcase. This region is called crankcase, where the crankshaft is located. So because of this, we will lose much of energy, when during compression and during expansion also we will lose energy. So in order to avoid that, we need to have some mechanism here which is achieved through a piston ring, which is fitted by compression. So if you have seen a piston ring, it will have a notch or opening on one side. So it is not a full circle, it will be open on one side, and it will always be open. So at a free state, if for a cylinder of say 100 mm diameter, the piston ring at free state will be like say 102 mm. So that means we have to compress it by 2 mm and then insert into the cylinder. So so there will be some constant force applied outward by the piston ring, and which will seal the fluid from going. It will prevent the fluid from going leaking through the piston.
So if it seals the fluid, then from intake valve, how the fluid comes inside the cylinder, sir?
Sorry, how the fluid comes inside the cylinder?
Yes, sir, inside the cylinder. Sorry, sir. I get it, sir.
Okay.
I get it, sir.
Hmm.
Sir, this piston rings is used for heat dissipation
No, no,
or not?
no. It is mainly used
No.
to seal the gas from going to the crankcase. And there are two piston rings, so there is totally three piston rings. So the last piston ring is generally called as oil scrap ring, and these first two rings are called as compression rings. So these compression rings are supposed to seal the gas in the combustion chamber, and the third oil ring is supposed to scrap the oil which is present in the cylinder valve. And when the oil goes into the combustion chamber and it starts to participate in combustion, we will get a lot of HC emissions and smoke coming out. So to avoid that, we have oil ring, and the first two rings is to prevent the gas from coming downward.
It means there is no relationship of the piston rings uh, in heat dissipation, right?
Heat dissipation, indirectly it has an effect, but its main purpose is not for heat dissipation.
Okay, but we have been asked in the assignment, sir, the function of piston rings inside the function of piston rings are like prevent piston from wear, dissipate heat to the cylinder, seal the cylinder, all of the above. So that's why I'm in dilemma. Which option should I take?
See, actually,
Though
which week this one is, sir?
first week,
First week is a deadline.
first week. Yes, sir.
Submission
No
date is
deadline. No, sir.
uh,
Submission date is not submission date. The last submission date is in 8th Feb, sir.
yeah, that is tomorrow, right?
Tomorrow.
So
Yes,
anytime
sir.
after tomorrow, I can give a brief explanation.
But we are in dilemma, na, sir. What should we write, sir? What should we take?
You
All
should
of the
write
above
the
or
best answer. You should not in an exam. You cannot ask the invigilator, right?
Sir,
Actually, we are
one
also
question
told that we
from
should
me.
not solve any problems that is in the assignment, which whose submission date is not yet done.
Understand.
uh,
Sir, one question from me.
Yes.
Yeah, as a what are the implications of using hydrogen gas in engine cylinder?
Uh, so
Any idea?
hydrogen, yeah. So generally, whatever we use is petrol, gasoline, or diesel,
Yeah.
which has hydrocarbons,
Mm.
which are C and H. For example, C8H18 can be the equivalent composition for this one for gasoline.
No, they are using natural gas, CNG, and all, right?
Yes, yes.
Similarly, can we use hydrogen? What are the implications of it?
Yes, the main advantage of using hydrogen is that we don't get a carbon dioxide, which is a
Yeah.
greenhouse gas. So
Yeah, that's okay. But how about the implications on combustion
combustion,
of it? Yeah.
combustion, it is a good fuel in terms of uh, combustion. You would be knowing the flammability limit of a fuel,
Mm-hmm.
which is a lambda. In terms of lambda, it will be like
Mm.
say 0.8 to 1.2 for
Mhm.
1.2 or 1.4 for the gasoline. So beyond,
Mhm.
if you go too lean and go too rich, the gasoline will not burn at all. So that is why we
Mm.
have a throttle to reduce the airflow rate when we want a
Mm.
low load power output.
Okay.
But
But,
in hydrogen,
yeah.
for hydrogen the flammability limit is like 5% to 95%.
Hmm.
So that means
Okay.
even when the mixture is too lean, the hydrogen can burn. And so this is
Okay.
advantage in cylinder, but outside cylinders this is a big disadvantage, because even when there is a small leak, it can catch fire.
Catch fire. Okay.
Yeah,
Okay.
unlike LPG,
Mhm.
you would be seeing
Yeah.
LPG.
Understand.
Yeah,
Understand. Okay.
after some point it mixes and it will not burn after it's mixed
Hmm.
properly.
So has it been tried, or is it like
Yeah, yeah.
is
Even in our lab, I'm from IIT Madras Ice Engines lab. In our lab, even in like 20, 30 years back, people have tried
Mhm.
hydrogen. They have run hydrogen engine as a part of MTech thesis work.
Mhm. Mhm.
So hydrogen alternate fuels, everything comes like a wave. Uh,
Okay.
yeah,
Mhm.
every 20 years,
Okay.
10 years, it keeps coming.
Okay. So even I am from Madras, sir. So
Ah,
is it
okay.
possible for me to meet you in your lab?
Yeah, yeah,
If
yeah, yeah.
yeah.
Uh,
Yeah.
you can take my mail ID.
Yeah.
My mail ID is not given anywhere. I think I have it right here.
No.
Okay, I have it right here.
So EPRADEV
Yeah.
at gmail.com,
Yes,
right?
yes, yes.
EPRADEV, right? Yeah.
Yes, yes, yeah.
E
Anyone,
Pradeep.
yes,
E Pradeep, yeah.
yeah, yeah.
Okay.
Anyone
Mm.
who has doubt on the problem can also put in the forum. I think you would be aware of the forum in the NPTEL portal, right?
Sir,
Sir,
can
what
you
is
please explain? Sir, can you please explain again the solution?
This problem, current problem.
Ji, sir.
Okay, okay. I will quickly go through this. We have given a single cylinder four stroke engine which runs with hydrogen in spark ignition mode, delivers a brake power of 20 kilowatt at 6000 rpm. The air gas ratio is given as 8 is to 1 and calorific value is given as 11,000 kilojoules per meter cube. The compression ratio is given as 8 is to 1 again. The volumetric efficiency is 70%, indicator thermal efficiency is given as 33%, mechanical efficiency is 90%. We have to calculate the cubic capacity of the engine. Now the brake power, we have brake power and mechanical power, so with this we can calculate the indicator power, which is 0.9 into 20, which is 18 kilowatt. Now we have indicator thermal efficiency, which is indicated power divided by fuel power. So here we have indicated powers already calculated as 18 into 10 power 3, writing in terms of SI units. And for fuel power, we have volumetric flow rate of fuel into calorific value of fuel. So with this we can calculate the volumetric flow rate of fuel that has to be sent inside the engine. So that is calculated as 4.95 into 10 power minus 3 meter cube per second. Now we have air gas ratio, and that means the flow rate of air to flow rate of fuel is 8 is to 1. So we can, with this we can calculate, with this and the flow rate of fuel, we can calculate volumetric flow rate of air, which is 39.6 into 10 power minus 3 meter cube per second. And now we have the both the gas flow rate individually. The total flow rate of the fluids in total can be calculated, and that was 44.55 into 10 power minus 3 meter cube per second. Now we know that the engine is running at 6000 rpm, so that means for every minute it is running, it runs 6000 revolutions. So that means for every second we will have 6000 by 60 revolutions. And since it is a four stroke
Yes, sir.
engine, we will have one cycle for every 2 revolutions. So that means in total we will have 6000 by 2 into 60 cycles per second. So that is 50 cycles per second. Now we had a volumetric flow rate of the fluid in total. So that was 44.55 into 10 power minus 3, and dividing that by cycle per second, we will get what is the meter cube of fluid that has to be sent in for every cycle. and that we have obtained as 0.891 into 10 power minus 3 meter cube. Now we have given the volumetric efficiency. So so with this volumetric efficiency is volume of the fluid that is going in divided by the displacement volume. So displacement volume is we can calculate displacement volume using these values. So that is 0.891 divided by 0.7 into 10 power minus 3, which is 1.27 into 10 power minus 3 meter cube. So this will be 1270 cc.
Yes, sir. Now it's clear.
Thank you.
Excuse me, sir.
Yeah.
Sir, how we get this PPT?
PPT will also be uploaded in a Google Drive, and you will get a link of that in the NPTEL portal. I think so far they haven't opened this page. Once maybe in the next week if they have opened, I can also show in the portal.
Sir, what is the scope of IC engine, sir, because of hybrid and EV?
Okay. I'm also working in hybrid powertrain for my PhD research. Hybrid powertrain, so currently we have seen many battery electric vehicles which is very unsafe, right? We have seen many accidents, fire accidents. So it will take some days or years to mature, and which will become very safe to use. So until then there will be a dilemma which one to go for. So ICE engine will stay there at least till that point. And also people say battery electric vehicles is green. This is based on assumption that the power source for the battery electric vehicle is renewable, or it doesn't involve any carbon dioxide or greenhouse gas emissions. But at least in India and many other countries, most of the power comes from coal power plants. So again, that battery electric vehicle is not actually green when you look into it. And so far we have seen battery electric vehicles only for up to passenger car and not for trucks. So at least in case of trucks and in case of ships, still the engine has to be there. That is what my feeling is.
Sir?
Yeah.
Sir, in Google Drive, where is the PPT?
No, I think you already have the link of the Google Drive.
So we have a link up for the joining section that are sharing by NPTEL.
You got a mail of it, is it?
Excuse me, sir.
So generally this will appear in this section. So you can see my screen, right? You can see the NPTEL portal on my screen.
Yes, sir.
Yeah, so
Yes, sir, yes,
it will, after the week's thing, here it will apply, like it will appear as a problem solving session, and if you click into it, you will get a link for the all the presentations and this one. I'm not able to get it now. So I think once maybe in few days you will get that link there. So then later you will be able to see yourself.
Sir, can you tell
Okay, sir.
more interesting fact about Formula 1 engine?
Formula 1 engine. What do you know about it? Maybe can anyone guess what would be the power output of this 1.6 kilowatt engine, 1.6 liter engine? Maybe first you can start guessing the 1.6 liter engine which we can buy outside. Maybe some commercial cars available. I think Honda City or something has 1.4 liters engine. The power output will be in terms of 1.5 liter engine might have 100 HP maximum, right? In case of F1 engine, it has 1000 HP. So you can see the scale, how they go about it. So they will most of the innovations for engines comes from them. So they because they do actual engineering, and they are able to spend a lot of money for their racing. Most of the technologies for the engine comes there first, like variable valve timing and uh, air spring for the valves actuation and so on, and then only it comes here. And they will have, for one tournament they will have some 5 engines in total, and they can, so after one tournament they all the 5 engines has to be scrapped out. That is the life of the engine. That's very low, but that is enough for their racing.
Can we use IC engine in rocket?
Ice engine?
Rocket.
I don't understand. Ice engine rocket too.
And space launch.
Space launcher. Space launcher. Okay. So when you go for space launching, you have to run an engine without air, right? Because in space you don't have air. So these are called air. These engines breathe air. So also in aerospace they have a terminology like air breathing engines and non-air breathing engines. So here this falls into a category of air breathing engine. So this cannot be directly used in a spacecraft unless when there is a oxidizer or
Cryogenic engines.
cryogenic engines like that. Yeah. Actually, one rocket will have many multiple engines for different auxiliary power appliances and so on. And I think I read about somewhere that there will be there could be some ice engine in some places, but for the main propulsion, ice engine cannot be used. Any questions, or will
Excuse me, sir.
sorry?
I have an query.
Yeah.
In ideal diesel cycle,
Yes.
it's let's say its completion ratio is like 20,
Mm-hmm.
and there is like there is return constant pressure energy addition CJs at 10% of the stroke. What does this statement mean, sir?
Again, is this an assignment problem?
Sorry, sir.
Is this an assignment problem?
No, sir. I just want to know the what this statement is trying to tell.
Okay. What is the statement?
Constant pressure energy addition
Okay.
CJs at 10% of the stroke. What does this statement mean?
Constant pressure heat addition. What at 10%?
CJs at 10% of the stroke.
CJs means? Can you spell it?
CEASES.
Ceases at sen. Okay, okay.
Yes, sir. Yes,
Okay,
sir.
okay, okay. So,
I just
okay. I have to check before coming. I think you might ask some assignment problem. Let me see.
what does this statement mean, sir?
Okay. Okay. So, generally the diesel cycle will be like this, right? We will have we'll start from here. This is pressure volume. We start from here,
Yes, sir.
and then compress. Then after compression we will have constant pressure heat addition, right? And then we will have expansion and then heat rejection. So that heat addition ceases at 10% of the stroke means this is the entire stroke, right? And then this is 10%. So if this is V, this is 0.1 V. With this you can calculate the ratio, what do you call, cutoff ratio, yeah.
Sir, would you mind explaining again?
Yeah, so this is the ideal diesel cycle, right? You can see in the bottom right corner. It starts with 1, where the volume is low and pressure is low. From there we start to compress. We have isentropic compression between 1 and 2.
Yes, sir.
And then we will reach a high pressure, but the volume will be very low. Now we have constant volume heat addition, right, between 2 and 3. And then so that is that means the pressure is constant,
Yes,
but the volume keeps on increasing because you add heat and then expand. And then after 3 you have 3 to 4 as isentropic expansion, right? Now the entire stroke is given by V1, stroke volume is given by V1 and V2, V1 minus V2.
Yes, sir. Yes, sir.
And when they say the heat addition ceases at 10% of the stroke volume, that means that 3 is at 10% of the entire V.
10% of the entire V.
Yeah, so V is V1 minus V2, right? So V3 can be calculated, which is 10% of 10% of V.
Sir, V1 minus V2, clear is volume. 10% of clear is volume.
V1 minus V2 is stroke volume, right?
V1 minus V2. Yes, sir. Yes, sir. Sorry, sir. Stroke volume is 10% of stroke volume.
Yes.
Okay, sir.
So that means this is 0.1 V and this is 0.9 V.
Okay.
Ready to see this problem? Okay, anyway, shall we move on to the next problem? Okay, we have two engines. Engine 1 is a 4-stroke engine, 4-cylinder SI engine, which indicated power is IP1, I write it as, is 40 kilowatt, and mean piston speed is given as 10 meter per second. And the second engine, which is a 2-stroke engine, 2-cylinder SI engine, whose indicated power is 10 kilowatt. Assume the mean effective pressure of both the engine to be same. Ratio of bore of the engine 1:2 is 2:1. Show that the mean piston speed of the engine 2 is same as that of the engine 1. So now that yeah, someone has raised their hand. Someone raised hand. I think you can unmute and ask the question. Okay. Okay, we have seen that indicated power is given as P MEP P MEP into LAN into NC divided by 60 into N, and this small n will represent a number of strokes per cycle. So for IP1 we have 40, which is PMEP into L1 A1 N1 into number of cylinders is given as 4-cylinder engine, and into divided by 60 into N. The small n is number of cycles per number of cycles for number of revolutions for one cycle, and that is for a 4-stroke engine it is 2, right? Yeah, 2. Now we have IP2, which is 10 kilowatt. Here the PMAP is given as same, so I write it as a same term, into we have L2 A2 N2 into earlier we had a 4-stroke 4-cylinder engine, now we have a 2-cylinder engine, divided by 60 into small n, which is 1 for a 2-stroke engine. So now I can write PMEP, I can equate PMEP for both the engines. So PMEP for the first one is 40 into 60 into 2 divided by L1 A1 N1 into 4. And similarly for the second engine, if I calculate the PMEP, it would be 10 into 60 into 1 divided by L2 A2 N2 into 2. Now we know that bore of the engine of say bore, I would write this as 1, B1 by B2 is equal to 2. So that means A1 by A2 is pi by 4 B1 square by pi by 4 B2 square. So this will be 2 square, right? So that is 4. So I can write A1 is 4 times of A2. Now bore of this is given, we need to calculate the mean piston speed. So mean piston speed is proportional to L into N. So we should have Ln together, and I think we have all other parameters. So we have 60, which can get cancelled. We have 2 and 4 and 2, which will become 2 in the denominator, and we have 2 here, 2 here. So this will become 40 and 10 will become 4. So we have 4 is equal to L1 A1 N1 divided by L2 A2 N2. We know that A1 is 4 times of A2. That means we have 4 L1 N1 by L2 N2. So this is equal to this. That means 4 get cancelled, and we have L1 N1 equal to L2 N2. So that means mean piston speed is I will write mean piston speed as MPS, which is 2 Ln by 60, right? So if I calculate mean piston speed of MPS of 1 will be 2 by 60 L1 N1, which will be same as 2 by 60 L2 N2, which is mean piston speed of 2. So finally both the mean pistons are both the mean piston speeds are the same. Are you able to follow this problem? Okay. If you have any questions, you can ask now, or can go to the next problem. I think we will not have time for this problem. Okay, if you have any questions about this problem or the previous problem or anything in general, we can discuss now. If you don't have any questions, I think we can close the session.
Excuse me, sir.
Yeah.
So why diesel engine produces more sound than petrol engine?
Yeah, I think you would have seen that the compression ratio for diesel engine is more than the petrol engine, right?
Yes, sir.
Yeah. Compression ratio of diesel engine is around uh, what value?
12 to 12 to 20. Yes, sir. 22, I guess.
Yes. And for
12
SI
to
engine?
22.
And for SI engine?
For SI engine, below 12.
Yeah, below 12. I think around 6 to 12, and modern engines will be like 8 to 12 or something. And
Yes, sir. Yes, sir.
I think it's till 10 only, not even 12. 12 is very advanced engine. Fine, anyway. Since diesel engines are more compression ratio, the in-cylinder pressures are very high, and the rate of pressure is also very high in case of a diesel engine. So this rate of pressure rise will correspond to the combustion noise directly. So that's why we hear more sound for diesel engine due to high combustion pressures engine. Not directly pressure, it's a rate of pressure rise is very high. Yeah. Yes.
Is any technology that engine that provided power?
Sorry, your voice is breaking. Hello, your voice is breaking. Can you repeat? Hello.
Yes.
Sorry, your voice is breaking. You can also write in the chat box.
Sir,
Yeah.
Which fuel has self-ignition temperature uh, higher, petrol or diesel, sir?
Um, which one will be having higher? You can guess.
Petrol.
Yes. Why?
Uh,
That is a property of
due to
the. So yeah,
that is the proper.
that is the property of the fuel, and that is the reason why we have spark ignition for when we use petrol as a fuel. So in terms of compression ignition, directly by compressing we will attain some temperature like 600 700 Kelvin, and when you inject diesel fuel, it should be able to combust within even in that temperature itself. So that's why we select a fuel for a CA engine which has low ignition temperature. In case of SA engine, we want to have some fuel which is since it is homogeneously charged inside, charge and air and fuel is both compressed together. It should have very high ignition temperature such that it will not combust even before the spark is given. That is the reason why we have a fuel of high ignition temperature for SA engine and low ignition temperature in CA engine. So someone has asked, is there is any technique that engine directly show brake power, indicated power, specific fuel consumption, etc. Directly show, so that means you don't want to measure anything and it has to show. Modern day engines is controlled using a ECU, so the engine controller unit knows the position of the throttle and throttle or the accelerator pedal, and also it knows the speed of the engine. So based on these two only, it chooses the fuel quantity and spark timing in case of SA engine, and fuel quantity and injection pressure and so on, based on these two parameters, engine speed and the throttle position or the accelerator pedal position. So if you have already made an experiment and found what is the brake power and indicated power and fuel consumption for all this at different points, speed and throttle or pedal position points, then in real time also the engine ECU can keep calculating these at real time, and somehow we can display it. If you know about OBD2, you can search about it, about OBD2 onboard diagnostics. I will write it somewhere. OBD. So this is on. So onboard diagnostics is some tool which communicates the ECU through CAN signals. You can also read about these two and you will get to know what it is. So through CAN signals it will read what the ECU have measured or ECU has calculated some basic parameters like engine speed, some temperature, engine coolant temperature, and pedal position, acceleration pedal position, and so on. So these many signals will be like, similar to these are there, and these will be sent through CAN signal to OBD device. So you can also see in the if you have a OBD receiver, then you can on live you can see what is engine speed, what is pedal position, and sometimes there will be something called load percent, which will be proportional to torque, and so on. And already in terms of specific fuel consumption, many new vehicles comes on the dashboard. You will be able to see the live KMPL, right? So that is based on the current amount of fuel that is injected and current power that is generated. So based on that, you get a live KMPL in new cars. Any other question? Okay. If there are no questions, I will close the session. I would thank everyone for participating. The video will be uploaded in YouTube, and the link will be sent to you in the and you will be able to access a link through the NPTEL portal. Thank you, everyone.
Thank you, sir.
Yeah, thank you.
Thank you.